Hello everyone. Today we're going to present our project on mental health prediction using the RHMCD20 dataset. To guide through our analysis, our presentation is divided into 4 parts. First, I will cover the background and literature review. Second, we will go through the data engineering and exploratory data analysis. Third, we will explain our modeling process and compare the results of the 10 algorithms. Finally, we will conclude with the real-world application and our final recommendations. As we know, recent global lifestyle disruption and isolation have contributed to rising psychological stress. This is a critical issue because rising stress is often a silent precursor to more severe anxiety and depression. Therefore, our goal is to develop a machine learning model to predict whether a person's stress level is increasing, specifically the variable growing stress. Timely intervention is crucial, so we want to identify these high-risk individuals as early as possible. We expect that models capable of capturing these complex behavioral changes will perform better than simple linear models. Before building our models, we look at 2 important studies to guide our research. First, depression risk exhibits strong heterogeneity, disproportionately affecting young adults and women. This suggests that demographic variables are highly priority features for our prediction model. Second, machine learning models achieve superior performance in depression risk prediction compared to traditional methods. Our primary research question is, can we accurately classify individuals with increasing stress level based on their behavioral and emotional changes? We hypothesize that a sample-based model will outperform linear models by effectively capturing the complex nonlinear interaction within the data. To test this, we implement a rigorous comparison of 10 machine learning algorithms. Our study provides 2 main contributions, validating the effectiveness of ensemble learning in this domain and identifying key behavioral risk factors to support targeted public health interventions.
After the introduction, we will move to data engineering. We use the RHMCD20 dataset, which consists of 824 observations and 13 variables. This dataset covers 3 main categories of features: demographics like age and gender, isolation factors such as days indoors, and psychological indicators including changes in habits. Let's look closer at our demographics. Our analysis shows a balanced gender distribution with 434 females and 390 males. Furthermore, the dataset includes diverse occupations, ranging from students and housewives to corporate employees. This diversity is important because it ensures our model is not biased toward a specific group of people. To ensure high-quality input for our models, we perform a regular 3-step data engineering process. First is data cleaning. We use the na.omit function to remove incomplete records, maintaining the integrity of our analysis. Second is target variable encoding. The original growing stress variable was in text format. We converted the target variable into a binary format to align with our baseline logistic regression model, and to focus specifically on identifying individuals with growing stress. Third is feature transformation. We converted all character variables into factors. This step ensures that algorithms like XGBoost can correctly interpret the categorical distinction in our data. Through exploratory data analysis, we examine the distribution of our target variable. For growing stress, the data contains 301 yes cases and 523 no cases. Although there is a slight imbalance, the dataset provides sufficient positive cases for the model to learn significant patterns. With the data now structured and cleaned, we will explain how built and compared our 10 machine learning models.
To find the most accurate predictor for growing stress, we systematically implemented and evaluated 10 different machine learning models. These models were selected from 4 distinct categories to test different mathematical assumptions. First, linear models like logistic regression and lossal logistic regression to check for simple direct relationships. Second, probabilistic models such as naive Bayes and LDA, which use probability to predict outcomes. Third, tree-based models, including decision tree, random forest, and XGBoost, which are excellent at decision rules. And finally, black box models, such as deep neural networks, SVM, MLP to capture hidden complexities. During the implementation, we encountered a technical constraint in the probabilistic category. We originally planned to use Gaussian bias. However, we realized a conflict. Gaussian model assume continuous models, but our data is heavily categorical. So, to fix this, we pivoted to linear discriminant analysis, which is also known as LDA. This adjustment proves that we didn't just run code blindly. We adapted our methods to fit the reality of our data. And to ensure our results are robust, um, we used a rigorous method called stratified tenfold cross validation. And we split our 824 data points into 10 parts. We trained each model 10 separate times and testing it on different segments. This process ensures that our accuracy numbers are reliable and unbiased. So, what did the evaluation show? Looking at the data, most models reached a performance ceiling around 63% accuracy. The results were very close. For instance, the simple logistic regression scored 63%, while the complex deep neural network scored 63%, 0.5. And on the lower end, the MLP struggled the most, finishing last with only 58.1%. XGBoost emerged as the top performer, achieving the highest accuracy of 63.8%. We attribute XGBoost's success to its superior ability to handle categorical factors and capture nonlinear interactions, something linear models missed. Now that uh, uh, we have our best model, let's look at what it discovered.
We have identified Charge Boost as our best model. We must answer the most critical question: what actually drives stress? We analyzed the feature importance extracted from our model, and the results provide powerful insights into human behavior during isolation. As everyone can see in the chart, the human one predictor is changes in habits. This means that disruptions in daily routines, such as irregular sleep or eating patterns, are the strongest early warning signs of growing stress. The second key factor is days indoors, especially the 15 to 30 days period. This suggests a critical window where isolation fatigue peaks. If a person has been quarantined for 2 weeks to a month, their vulnerability skyrockets. Interestingly, gender male also appears as a top factor, indicating that men might be less expressive about their stress, making detection harder but more crucial. How can we translate these findings into real-world impact? We propose implementing a stress early warning framework for public health. Our model optimized the screening process, allowing healthcare institutions to focus only on high-priority indicators. They can simply focus on the two key risk factors we identified: habit, habit stability, and isolation duration. Using our Charge Boost model, we can effectively screen for high-risk individuals, especially those in the 15 to 30-day isolation window. This allows for targeted interventions, ensuring that medical resources and psychological support reach those who need them most before stress escalates. Thank everyone. Thank you.